Hello everybody, my name is Gautam and through this presentation I am going to explain to you how Kalman filters are used in sports. If you have watched sports recently, let's say anytime in the past 20 years or so, I'm sure you would have come across this technology. It's called the Hawkeye. As a sports person and computer science major myself, it brings me great joy and excitement to explain to you the real world application of a core mathematical computer vision topic in the world of sports. What's the most crucial decision made in sport? Whether a batsman is out or not out, whether the ball has pitched on the line or not, whether it be the ball or the shuttle, whether the ball has passed the goal post or not. Human umpires or referees officiating these matches have a single attempt to watch it happening, and they might be wrong at times. In order to improve such decision making, we need to track the trajectory of the ball and at times also predict its path in case of occlusion, particularly here in cricket. This is where the Kalman filter shines. It operates in a continuous two-step loop, predict and update. Once the ball has been released, the physics engine makes a guess or a calculation on where the ball should be at the next time instant. It takes the ball's current speed, velocity, temperature, air pressure, gravity, and makes a mathematical prediction. Alas, but only if it were that simple. There is wind, there is rotations on the ball, the condition of the ball changes, there are other aerodynamic forces acting on the ball apart from just drag. And such factors greatly affect the trajectory of the ball. I will show this to you in the future slides, but continuing with what the update step is. The ball's real world position is captured using high speed, high resolution cameras that are located around the ground, 6 in case of cricket and 10 in case of tennis, through triangulation and epipolar geometry at the instant the frame was captured. This makes up our measurement. The Kalman filter then takes the calculated position and combines it with our observed position based on the confidence we have in each, and also updates the physics model as a result. Confidence in the calculated position varies in different regimes of flight of the ball, whereas confidence in observed positions by the camera may be affected by things like motion blur or pixel errors. Basically, the Kalman filter balances what the math expects versus what the camera sees. To do this, the system needs to maintain a state. In Hawkeye, the state vector represents everything we care about, be it the position in the x, y, and z coordinates, or the velocities in these three coordinate systems too. So, just like tensor manipulations we often use in computer vision libraries, the Kalman filter relies on matrix operations to transition the state from one time step to the next. It's important to understand that the system doesn't actually know anything at the start. It doesn't know who's bowling or how fast they're bowling or where the ball is being released from. It only waits for the camera to detect a ball-like object, and from the first two frames, it calculates its initial prediction, the initial position and velocity. From there, the transition matrix, a rule of physics, takes over to predict the next 1/100th of a second in a loop over and over again. Now, let's come to the update step. Our cameras provide a measurement vector, okay? Let's call this Z. The cameras don't see velocity really, they only see a position. So we use measurement matrix H to map our high dimensional state down to simple coordinates the camera can verify. This is done again through triangulation and mapping 2D coordinates that are observed from the camera's frames down to a physical 3-dimensional world that corresponds to the ground. When we compare our prediction to our measurement, we almost always find a small gap. This is called the residual. Okay, maybe the ball swung, maybe it didn't bounce as much, or maybe the camera had a tiny bit of noise. The Kalman filter doesn't panic when it sees this gap. It uses it as data to refine the next prediction. Let's say the ball hits a crack on the surface of the ground, or if the pitch is particularly dead. This is where the residual plays a crucial role in updating our laws of physics. Let's say if there's a discrepancy, the Kalman filter doesn't just ignore it. It uses that error to instantly update its understanding of the ball's spin and the pitch's bounciness. It's essentially a physics engine that learns the conditions of the match in real time. This brings me to the question, how much should we trust the camera versus how much should we trust physics? Let P be the uncertainty in your prediction and R be the uncertainty in our sensor or camera in this case. If R is huge, let's say it's a bad camera, then K becomes very small and the filter ignores the camera and purely works on the physics-based prediction. This brings us to the brain of the algorithm. Okay, the Kalman gain, denoted as K, So our data is never really perfect, right? Our cameras have some sensor noise, maybe poor lighting, or the ball is moving too fast for the shutter to capture accurately. On the other side, a physics model has process noise, like a sudden gust of wind or low bounce that we didn't account for. We represent this as P. The Kalman gain is a value between 0 and 1, okay, that acts like a trust slider. If the camera data is clear and reliable, K moves towards the camera. If the camera is struggling and the ball's trajectory has been consistent for the past 50 frames, K moves towards the physics side of the prediction. It calculates mathematically the optimal way to combine these two sources of information to minimize our overall error. This is an intuitive way to understand how it comes up with K. So let's say our observations, we have a high degree of confidence depicted by how narrow this Gaussian curve is, and our physics-based model, we have a slightly lower confidence in it depicted by the slightly wider Gaussian curve. And the Kalman gain combines these two effectively. Note how the final result is closer to the camera's observations because it had a greater confidence. Now let's look at the defining moment of what Hawkeye is in cricket, the occlusion. Note here in the first image that the ball has been released by the bowler and the high-speed cameras are tracking the ball at every frame. I have encircled it here so that you can clearly see it. And here are the two Gaussian curves from the previous slide which show that we have equal confidence in both the physics-based calculation as well as the camera, and we combine them equally. In this particular image, the ball has just impacted the ground. Here, we reduce the confidence in our physics-based model because, like I mentioned earlier, the ball tends to behave randomly when it bounces on the ground on a lot of occasions. So we have greater trust in our observations. And note here that this is where the ball had bounced and this is where the ball currently is. And like the physics-based model, the batsman too assumed that the ball might have traveled along its own merry path in this particular way, right? That's what we saw here. The ball had been released from somewhere here and it is traveling in this direction. But after bouncing, it pitches and moves into, or rather towards the batsman and hits him on the shin, right? So here, at the time of occlusion, we no longer care about where the ball is. In fact, if you look closely, the ball is here, but we don't care. We need to figure out whether the ball would have hit the stumps had it not been blocked by the batsman's body, right? That is what it's a way how a batsman can get out. It's called leg before wicket, where the umpire has to judge whether the ball would hit the stumps had it not been blocked by the batsman, right? And if the umpire is not able to make a decision, the Hawkeye system does it. So here, as you see the blue portion, that's the path that has been estimated by the Hawkeye system. And at this point, we lose complete trust in our observations, and we rely solely on the physics model that had been continuously updating itself based on the pitch, based on the swing, or based on the movement. Here, like for example, the lateral movement at this point was drastically adjusted, and it will continue to follow this in this blue stretch of the trajectory also. And in the end, this is how the decisions are made, and this is how accurate the system is. And this is the result that you see during a TV match. The virtual path isn't just a mere guess, it's a statistically optimized prediction. By using the Kalman filter, Hawkeye bridges the gap between raw computer vision, which only knows what pixels are and what a ball might look like on an image, and physical reality, which knows only the kinematics equation. And in the end, this combines it all and helps us make a multi-million-dollar sports decision with mathematical certainty. As I was mentioning earlier, a ball that was released from here, had it not been affected by any other aerodynamic forces, would have followed this trajectory, the purple trajectory. But it is acted upon by aerodynamic forces, which we call swing in cricket, and this is the path it actually followed. It swung laterally. Another instance is here, where it bounced off the wicket, and if this is not clear enough, it says it deviated an entire 3.9 degrees, which led to a difference of 42 centimeters when it reached the batsman. With this, I would like to conclude by sharing the story of how this technology came into being. It was invented by Dr. Paul Hawkins at Roke Manor Research in England. And what motivated him to come up with this technology was that he was given out in a local match. He was an amateur cricketer and he was given out for a contentious LBW appeal. And he felt that it was unfair, and that's what made him set out to come up with this technology. And guess what? 20 years down the line, it's used in over 20 sports use it at the highest level with a great degree of trust in the system. I come to the end of my presentation. I hope you had as much fun as I did in learning about the system that we see in sports every day, or learning how a theoretical concept is actually applied in the real world. Thank you so much for your attention.